right, for the machine problem, first of all, let's just set up the situation. And then we'll see, I've already got the graph up there, but we'll see how I got to that graph and then how we're going to use it. But on this problem here, they talked about the cost to run machine 1 for an hour is $2. During this hour, machine 1 produced 240 volts and 100 nuts. The cost to run machine 2 for an hour is $2.40. During that hour, machine 2 can produce 160 volts, 160 nuts. So with a combined running time of no more than 30 hours, how long should each machine run to produce an order of at least 2,080 volts and 1,520 nuts at a minimum operating cost? So this was a little bit different because we wanted to minimize our costs. Well, because cost is what we're going to answer, the cost was really based on how long or how many hours each machine was going to run. So to start with our variables here, I made X the hours for machine 1, and I made Y the number of hours for machine 2. Because again, eventually the cost is going to be based on how many hours the machine is going to run. All right, so limitations here. More limitations are based on, first of all, depending on how many hours you run the machines, how many volts are we going to produce? How many nuts are we going to produce? So let's start with the volts. Well, machine 1 was going to produce 240 volts. So 240x plus machine 2 is going to produce 160. And we want to make sure that we run the machine long enough to produce at least 2,080. So that means we need to equal 2,080 or exceed 2,080. So a lot of the problems we've been doing so far have been less than situations. This is a greater than situation. Same deal with the nuts. We're going to have 100 for X. We're going to have 160 for Y. This time we need to be greater than or equal to 1,520. So those are kind of our limitations for what we are producing. In each case, we got to make sure we produce enough. Another limitation we have is based on our time, because we said the combined running time can be no more than 30 hours. So however long X runs plus however long Y runs has to be less than or equal to 30 hours. And then the extra parts that we usually have, since we're talking about hours, we need to stay positive or equal to 0. So X is greater than or equal to 0. Y is greater than or equal to 0. And you may be saying, well, why are those two things important? Well, the biggest thing is that restricts us to the first quadrant. All right, so if we try to graph these things, and again, I've already put the graph on here, but since we're in the first quadrant, I would again suggest looking at X and Y intercepts, seeing where they're at and using that to help us out. But if I look at the 240X plus 160Y had to be greater than or equal to the 2080, I'm going to have that graph that has a y-intercept of 13. So that was this graph here. I'll use a different color there. See it? There we go. All right, so we have that graph there, and then that was greater than, so we had to shade above it. We've got the other graph where the y-intercept on this one was at about 9.5, so that was this graph here. We have the X, and we would be shading above that one. We have the X plus Y is less than or equal to 30, which means the y-intercept was 30, and so is the x-intercept. This number shading below. And then we had the fact that it had to be greater than 0 for x, which means I'm limited by the y-axis. And I was going to shade to the right of that. We have that y had to be greater than or equal to 0, so I'm going to be shading above that. So ultimately, I end up with this shaded region. So that's our feasible region. Well, within that, I now want to test out the points. But before we test out the points, we need to have a function to work with. So remember what the question asked. The question wanted to know the minimum operating cost. So our function should deal with cost. Well, they said the cost to run machine 1 was $2 an hour. The cost to run machine 2 was $2.40 an hour. So our function for this is f of xy is equal to 2x plus 240y. All right, now we need to test points. Let's see how many points we have for our feasible region. Well, we're really looking at the vertices of this shaded area. So I got 1, 2, 3, 4, 5 different points that I'm going to look at. Of those 5 points, 4 of them are either on the x or y axis, so those would be fairly easy to find. The 5th one would be where we intersect with those 2 inequalities. So with Desmos, that's not too bad. If we want to do it algebraically, we'd be back to doing some sort of system of equations. But what you should have found would be these points. The point 15.20, the point 30, 0, 0.30, 0.13, and that intersection was at 4.7. And so you're going to plug all those values in. Plug in the x for x, plug in the y for y, and these are the different prices we end up with. This one we had $30.40. This one was $60. This one was $72. This one was $31.20, and this one would have ended up with $24.80. And so I look at all these and I find out, okay, the one that had the minimum operating cost was this one here that ended up costing $24.80. So answering the question, I need to run machine 1 4 hours and machine 2 for 7 hours.